How you doing today? Good. Good. Alright, so today we're going to start our discussion for chapter 3 and 2. In chapter 3 we are discussing the cell. What we're going to be covering in this chapter, we're going to have an overview of the cells, the structure of the cell membrane. We're going to be describing the different types of membrane transport, cytoplasm and organelles, and then at the end of the chapter we're going to be discussing the nucleus and the cell cycle. Let's start with the cell diversity. So we don't have a single type of cell. We have different types of cells that will form the different tissues that we did see back in chapter 4, if you remember. We did see cells that will be forming the linings and coverings as well as the glands. Those are like my epithelial cells. We did see cells that will have the ability to contract, like my muscle cells, skeletal muscles, smooth muscles, or cardiac muscle cells. We did see cells that have the ability to store fat, like the fat cells and the adipose tissue cells. We did see cells that will have the ability to conduct electrical impulses between the different organs, like my neurons. We did see cells that can fuse together and to form embryo. Those are like the sex cells or the gametes, like the sperms and oocytes. So we have diversity of cells. We don't have a single type of cell. Each cell will be carrying a specific action according to its structure. The general structure of any cell will be formed of a cell membrane that will form the outer boundary. Inside this cell we will have the cytoplasm. This is a fluid containing organelles, and at the center of the cell, the control center of each of those cells would be the nucleus. So any cell would have plasma membrane, would have cytoplasm. Inside this fluid, we do have organelles, and at the center of the cell that would be controlling everything that will be taking place in the cell, this would be my nucleus. This is how a cell will look like. As you see, forming the outer boundary would be my cytoplasmic membrane. Inside you have many organelles inside fluids. This is my cytoplasm. This is my control center. This is my nucleus. So let's discuss here the plasma membrane. The plasma membrane is forming the outer boundary of the cell. It separates the outside from the inside of the cell. So we call the outside, this is my extracellular fluid. Extra means to the outside. And to the inside of the cell we have what we call the intracellular fluid. So the plasma membrane is separating the extracellular fluids that we do have on the outside surface of the cell, and the inside we will have intracellular fluid compartment. So we have two types of fluid. Fluid either outside of the cell or inside of your cells. Again, fluid outside, this is called extracellular fluid, and fluid inside of the cells, this is my intracellular fluid. Your plasma membrane will be formed of two major chemical structures. We have lipids and proteins. First type of lipids that will be forming around 70% or representing around 75% of the lipids of your plasma membrane. This is called my phospholipid. How the phospholipid looks like? The phospholipid, from its name, it's formed of phosphate and lipids. Here we will have fatty acids. Phospholipids. The plasma membrane is formed of a phospholipid bilayer, so you have two layers of phospholipids arranged in this way. Phosphate groups would usually be charged. I have a charge on me. And fatty acids are non-charged, no charge. Generally speaking, general chemical concept, any charged particle will love water. It can dissociate in water. It is water soluble. Any non-charged particle, this is like the lipids, for example, I hate water. I am not lipids, I am not water soluble. So for the phospholipid, I have two parts. I have phosphate and fatty acids. Phosphate will love water, so I will call them hydrophilic. And they will be directed towards water. So you have water on the outside of the cells. This is my extracellular fluid. And you have water to the inside of the cells. This is my intracellular fluid. So phosphate is usually directed to the outside of the plasma membrane, whether towards the outside of the cell, where you have extracellular fluid, or to the inside of your cell. This is my intracellular fluid compartment. I love water. I am hydrophilic. Compared to the fatty acids, those fat groups, they are hydrophobic. What's phobia? Fear. Hydro is water. So I'm afraid of water. So I will be directed away from fluid. I will be directed to the inside of the plasma membrane. Away from water. Away from the extracellular fluid on the outside, and away from the intracellular fluid on the inside of my cell. I will be directed to the inside of the plasma membrane. So you see here, I have hydrophilic parts. Those phosphate groups will be directed towards the fluid. They love water. Philia is love. Hydro is water. So phosphate groups are hydrophilic. They will be directed towards the fluid, whether outside or inside, and extracellular fluid or intracellular fluid compartments. This is how the phospholipid bilayer looks like. It gives you a mosaic shape appearance. Phosphate groups on the outside, fatty acids on the inside. Another type of fats that would share in the formation of your plasma membrane would be cholesterol. You see those yellow parts here on the plasma membrane. So this is my cholesterol. The cholesterol here, what will give you the fluidity and the stability of the membrane? What do you think? Is the plasma membrane something fluid, or is it stiff? Solid. Like if I did have a trauma to some of my cells, will all of them rupture, or they can accommodate this trauma? They have some fluidity.
Well, you said it loves the water.
So I'm talking about the plasma membrane. Is it solid or is it fluid? It's fluid. What gives the plasma membrane its fluidity would be the cholesterol particles entering in its structure. It makes it fluid. Another type of fats that we're gonna see in the forming and sharing in the formation of the plasma membrane would be my glycolipids. Glyco is sugar. Lipid. So this is a sugar group. So sugar groups attached to fats. Glycolipids will share in the formation of what we call glycocalyx. What's glycocalyx? This is the fingerprint of your cells. So if you did give me some of your cells to be implanted in my body, what can happen? Or if I got an infection, a bacterial cell did pass to the inside of my body, what's going to happen? My immune system will start to recognize that those are not my cells and will start to kill them. How did my immune system figure out that those are not my cells? Because simply you're carrying a fingerprint on your cells. What represents here is the fingerprint of the cell are the sugar groups attached to the proteins and the lipids of your plasma membranes. All those sugar groups all together will form what we call glycocalyx. This is my glycocalyx. Glycocalyx. So again, what's forming the fingerprint of your cells? What's forming this glycocalyx that will determine the identity of your cells will be the sugar groups either attached to proteins or lipids. What did we call the lipids attached to sugar groups? Those are called my glycolipids. Glycolipids. So again, three types of lipids that we can see forming our plasma membranes: phospholipids, glycolipids, and cholesterol. Another chemical structure that will be forming my plasma membranes will be proteins. Proteins will be either integral proteins occupying the whole thickness of the membrane, like what you see on here. Those are integral proteins. Or they might be attached to integral proteins either to the outside surface of the cell membrane or to the inside surface of the cell membrane. Those are called my peripheral proteins. So you have integral proteins and peripheral proteins. Again, what's the difference? Integral proteins, they are integrated within the cell membrane. They are occupying the whole thickness of the plasma membrane. Compared to peripheral proteins, from the name, what can you understand? They are located peripherally. They are attached to the outside or to the inside of your plasma membrane. Integral and peripheral proteins. Why do you keep proteins within your cell membranes? They are acting as enzymes, they are acting as receptors, they are acting as transport proteins. What this means? What's meant by a receptor? To receive something, yeah, right?
Yes.
What are you receiving here? Through in your cells. You're receiving commands. So for example, if you got a chemical message called insulin, what you're going to do as a cell, you will be picking up the glucose to the inside of the cell. This is what you're going to do. So again, here, in order for a chemical signal, like the hormone, to have an effect on your cells, it has to bind to a receptor. What's forming your receptors of the cells will be proteins or lipids? Proteins. So you have proteins in the cell membrane to allow the transduction of the chemical signal coming from outside to have an effect on your cell. Acting as an enzyme. What's an enzyme? This is something that will be accelerating the chemical reaction. So for example, insulin. What's the effect of insulin, for example, on my fat cells? Insulin is helping you to store the excess glucose inside your adipose tissue cells as fat, as triglycerides. So you start to accumulate fat. So when I eat, if I have glucose that I don't need to form energy, to produce energy by, I will get this glucose to the inside of my fat cells and will transform it into fat. So how would you do this? You need to pass through chemical reactions. What will allow you to accelerate those chemical reactions? What will allow you to perform those chemical reactions will be proteins acting as enzymes to perform a chemical reaction. I need to have enzymes. What if I'm willing to get, for example, sodium from outside to the inside of my cell? What if I want to get potassium from inside to the outside of the cell? I need to transport something from inside out, outside out, in. I need to move a substance across the cell membrane. How would I be able to do so? I need to move them through protein. Those are transport proteins. As we're going to see in a minute, some proteins will act as channels, some proteins will act as carriers according to the type of substance that you would need to transport. So for example, if I'm wanting to get water, I would have proteins called aquaporins. Aqua is water. Porins, this is a protein that will form pores. So those are protein channels that will allow the transport of water. So again here, major functions. We're going to be discussing the functions of the proteins in a minute in much more detail. What about the peripheral proteins? What's the function of having, why would I have a protein attached to the integral protein on the outside or the inside surface? It maintains the integrity of the cell. In your cells you have skeleton formed of protein fibers. So forming my skeleton, forming the cellular skeleton, you have protein fibers like this. And on the outside of the cell, you will have other protein fibers. What allows you, first before we get to this, I need to ask you a question here. So is the plasma membrane attached to the structure, internal structure of your cells? What do you think? If this is my plasma membrane, here, this is my plasma membrane, and this is the internal skeleton of the cell, are those attached together? They go with each other, or they are not attached to each other? They can move separately.
They're not.
Which one?
They're not attached.
They're not attached. They are attached. Alright, so actually they are attached together. So the plasma membrane is attached to the skeleton of your cells. Also, it's attached to the outside. So what this means, that the inside of the cell is attached to the outside, yes. That's why you don't wake up in the morning having your ear away from you, for example, or you drop your nose. All your cells are attached together and attached to the protein structure that surrounds those cells. This is what maintains the integrity of the cells, allowing the cells to get attached together, cell-to-cell link. Also, some of those proteins, again, will have sugar groups on the outside surface. Have sugar groups. What do we call them? What do you think? What's a sugar group? Glyco, and this time is attached to a protein, not fat. So this would be called my glycoprotein. And again, why do you need glycoproteins and glycolipids? Why do you need glycoproteins and glycolipids? Why do I have sugar groups on my cells? To be sweet?
Energy.
To store the fat, to
Cell-to-cell recognition. Remember, those are the fingerprints of your cells. Fingerprints of your cells. If you give me blood cells of yours and we don't have the same blood group, what's going to happen? My immune system will start to attack the transfused cells. Why? Because I was able to recognize that those are not my cells. Those are non-self cells. How did I know? I did check the ID. What will form your ID is glycoproteins and glycolipids. Forming together your IDs, this is called my glycocalyx. Glycocalyx. Alright, is the glycocalyx concept is clear? Yes? Again, what's glycocalyx? This is your ID by which you will be identifying if this is your cell or not. Determining, are those cells or non-self? Is this a bacterial cell invading my body? Are those transplanted cells coming from outside? I will start to attack them. Alright, what is the outer covering of the cell called? Is it nucleus, cytoplasm, or plasma membrane? Plasma membrane. Plasma membrane. Moving to the functions here of the proteins. First function of the protein is transport. I'm acting as a transport protein. I'm allowing a substance to pass from inside to the outside or from inside to the outside of the cell. So the first function here for the proteins is to allow transport across the cell membrane. Another function of the protein would be to act as a receptor. And again, why do I need receptors? For an extracellular signal to have an effect on the cell, it needs to bind to a receptor. As what we mentioned with insulin. Insulin will need to bind to a receptor for your cells to pick up the glucose to the inside. Your cells will not pick up the glucose from the blood unless you have insulin. and unless you have a receptor. Either you don't have insulin, you don't have the signal, or I don't have a receptor for the insulin. And as a result, I will have a high blood glucose level. I will have diabetes. Either I don't have a signal, insulin, or I don't have the receptor for the signal. So in both cases, I'm not able to pick up the glucose to the inside of my cells. Again, what will act as a receptor for your cells will be your plasma membrane proteins. Another function here for the plasma membrane proteins would be to get attached to the cytoskeleton of the cell as well as the extracellular matrix. I'm attaching here the cytoskeleton of the cell and the extracellular matrix, and this is what will maintain the integrity of my tissues, what will keep them integrated and attached to each other. Another function here for the protein is to act as an enzyme, and as we've mentioned, what is an enzyme? This is a chemical catalyst. For any chemical reaction to take place, you will need enzymes to facilitate the chemical reaction, to speed up those chemical reactions. Again, like what we mentioned about insulin on your adipose tissue cells. What is the function of insulin on your adipose tissue cells? They will enhance the transformation of glucose into fat. So I will need membrane proteins to allow the transformation here to take place. I am acting as an enzyme. I will be activating intracellular proteins to act as enzymes. Another function here will be intercellular joining. I'm attaching the cells together. And last function here for the membrane proteins will be to allow cell-to-cell recognition. Again, how do you allow cell-to-cell recognition? By what? What do we call the sugar groups here? All the sugar groups together, this is called my glycocalyx. If you have sugar groups attached to proteins, those are called my glycoproteins. If they are attached to lipids, those are my glycolipids. How do you attach the cells together? We have three types of cell junctions. If you see on here, the first type is like making stitches between the two cell membranes of two of the adjacent cells. So protein filament is passing from one cell membrane to the other, from one cell membrane to the other. This is called my tight junction. And what do you think when you hear tight junction? Do you have a lot of spaces between the cells, or those are closely attached, adhered together? Closely attached. They are closely attached. You don't have much spaces between the cells. And where do you think I will need tight junctions? In what organs? Or in other words, where would you need nothing to pass between the cells, and you need everything to pass through the cell? You need something to pass through between your cells of the skin, of the epidermis? Yes or no? Do you need something to pass freely between your cells? Yes or no? So do you want, for example, if you're swimming in the pool, to swell? Yes or no? No. So I want to prevent everything from passing through my skin. So I will have what kind of junction between the epidermal cells? Tight junctions. If you did eat, do you want anything to pass to your bloodstream, or just what you did break down? That's what I did break down. So I will need tight junctions in between my small intestinal cells. I will only allow the absorption to be taken place through the cell and not between the cells. I need a substance to pass through the cell to the blood and not between the cells. That's why I will have a tight junctions between my cells. Another type of cell junctions will be like having plates and screws in between. So you will see you have a plate here in this cell, and you have another plate in the adjacent cell. Those plates are attached to the cytoskeleton of each cell. And you will be attaching the two plates by screws. And those screws are formed of sugar particles. Those screws here, those are called my linker glycoproteins or cadherins. This cell junction is called my desmosome. Desmosome. So again, how do you attach two cells by desmosomes? On this side, I will have a plate of protein which will be attached to the cytoskeleton of this cell. On the other cell, I will have another plate which will be attached to the cytoskeleton of the adjacent cell. I will be attaching the two proteins by glycoproteins, or what we call cadherins, and this will keep the cells closely attached together. It's like using plates and screws in between. Another type of cell junctions would be gap junctions. And from the name here, what comes to your mind first? Do you have a lot of spaces between the cells, or those cells are closely attached together? You have spaces, and this is wrong. Alright? Alright? Those are still junctions. I'm still attaching the cells. But what I mean by gap junction here, that you're attaching the cells by channels. You're closely attaching the cells together, but this time you're attaching them by protein channels. This is what I mean by gap. Why do you think you will be attaching cells by channels? Connections. Why do you reduce the effect of your plasma membranes on here? Why are you reducing the effect of the cell boundaries? It's like dissolving the boundaries between countries. So in the European Union, for example, they did dissolve the boundaries. So people can travel freely between the countries. They can trade freely between the countries. So same concept here. Why would I have gap junctions? To reduce the boundaries between the cells. When do you think you will need to reduce the boundaries between the cells? All the cells will need to act as one unit. Remember, what kind of cells did need to act as one unit that we've mentioned back with the tissues? The tissues. So try to imagine this is my heart. Alright, I did answer the question already. Alright, so this is my heart. So if you contract those cells, and then those cells, and then those cells, and then those cells, and then those cells, will you have an effective cardiac muscle contraction to pump the blood out of your ventricles? Yes or no? If you contract each cell separately, I won't have an effective contraction. So how I will solve this? I need to reduce the boundaries between my cells. For when I get an electrical impulse to one cell, it can travel freely to the other cells. So all the cardiac muscle cells will be receiving the electrical signal in the same time for them to contract as one unit. I don't have boundaries, real boundaries between my cardiac muscle cells, because I want my cardiac muscle cells to contract in the same time as one unit. I don't want the signal to reach this cell before this cell before this cell. I need the electrical impulse to pass freely to all my cardiac muscle cells, for all of them to have to contract in the same time as one unit. Do you remember how did we see the gap junctions under the microscope when we studied the cardiac muscle tissue? This is something that you did have in your last tissue test.
Mm.
Those dark lines between the cardiac muscle cells were called between. So this was 2 days ago, right? What did we call those dark lines between the cardiac muscle cells? Intercalated discs. What are those intercalated discs? Those are my gap junctions. Those are the proteins between the cells that will allow the conduction of the electrical impulses between the cardiac muscle cells. Those are my intercalated discs. Here we go. Again, what are those intercalated discs? Those are the protein channels located between the cardiac muscle cells. Again, what kind of junction do you have in your cardiac muscle cells? Gap junctions. Gap junctions. Moving on to the membrane transports, how I will be able to transport a substance to the inside or to the outside of my plasma membrane. We have two types of transport. We either have passive transport, in which I don't require energy for it to take place. I don't need energy to transport the substance to the inside of the cell or to the outside of the cell by passive transport. Compared to an active transport, I am moving a substance using energy. I require energy to move the substance. Moving on to the types of passive transport. Types of passive transport. So if this is my cell membrane on here, I want to move substance X here from outside to the inside of my cell. A general rule, any substance can move on its own down its concentration gradient. What I mean by concentration gradient, this is the difference between the concentration on two sides of the membrane. So here I have a membrane in between the two sides. A substance X will pass from its high concentration gradient down its concentration gradient, means from high concentration gradient to a low concentration gradient. This is anything will pass from a high concentration, from a high pressure to low pressure. Alright? Do you need energy to pass a substance from a high pressure to a low pressure? Yes or no? No, I don't. No, I don't. I will give you an example here. If I told you we're gonna all stay in this space next to each other. Only this part of the room. Alright, we'll be closely next to each other. Alright, would you prefer to stand here or to move around in the room?
Move around.
So if I give you the choice, either to stay in this small space or to move all around in this room, would you prefer to stay in here or to move back to your places? To move back to your places. Did I give you something to go back to your spaces? Or did you prefer to do this on your own?
On our own.
You did prefer to do this on your own, right? What if I told you that everybody who will be staying here will get 5 extra credits in the next test? What are you gonna do?
Camp out.
So you will come and stay all here, right? This is an active transport. I need to pay you to do it. Alright, this is the difference. So generally speaking, if you're moving from a high concentration gradient to a low concentration gradient, I don't have to give you any extra points, right, to do it. You will do it on your own. So this is a passive transport. You're passing from high pressure to low pressure, from high concentration to low concentration. But if I want you to do the opposite. I want you to move from a low pressure, from your places to this small area with higher pressure. Would you do it on your own? Would you prefer it? No, you won't. But if I did give you energy, if I did give you extra credit, will you do it? Yes. This is the difference here between a passive transport. You do it on your own. You don't require energy to do it. You're moving a substance from high pressure to low pressure, high concentration to low concentration. Another factor that will share in determining the type of passive transport will be the type of substance that we are trying to move from a high concentration gradient to a low concentration gradient. If this substance is lipid soluble, if I am lipid soluble, I can pass by a type of passive transport called simple diffusion. So I'm passing through the phospholipid bilayer from a high concentration gradient to a low concentration gradient. I can pass through the fatty acid tails. I am lipid soluble. I don't carry a charge. Do you remember? Are the fatty acid tails hydrophilic or hydrophobic? And they are hydrophobic. They hate water. They hate charge. But they will allow any lipid substance to pass. So if you're trying to pass a lipid-soluble substance, it will simply pass by simple diffusion. It will pass from its high concentration gradient to its low concentration gradient through the plasma membrane. What if you are trying to move sodium? Let's say I have a charge. Am I lipid-soluble? If I have a charge, am I lipid-soluble or water-soluble? Water soluble. You have charge, you're water soluble. You cannot pass through fatty acid tails of the plasma membrane. I cannot pass by simple diffusion. So how would you pass sodium from its high concentration gradient outside of the cell membrane to its low concentration gradient that inside the cell membrane? What you're going to do, you will need a channel, a protein channel to pass through. What if, for example, you have a large protein? Protein will have a charge. Are you lipid soluble as a protein? Yes or no? Are you lipid soluble? Do you have a charge? Yes. If I have a charge, am I lipid soluble? Yes or no?
Yes.
No. So again, for those who are still confused, if you have charge, you're water soluble. And if you're water soluble, you're lipid insoluble. And if you don't have charge, you're water insoluble and you're lipid soluble. Keep it simple that way. If you are lipid soluble, will you be able to pass through the plasma membrane? Yes or no? Yes, I can. I am lipid soluble. I can pass through the fatty acids. What if I have charges? I have a charge on the outside surface. Will I be able to pass through the plasma membrane? Yes or no?
No.
Yes or no?
No.
Is the rest? Who did got lost? Right. So again, if you have charge, will you be able to pass through the plasma membrane? Yes or no? No. Right. You have all to say no. All right. There is no other choice. Right. If you have a charge, you're lipid insoluble. and you cannot pass through lipids. You are lipid insoluble. You cannot pass through the plasma membrane. You have fatty acids. It's a big molecule. It's not able to pass through the plasma membrane. It's not able to pass through channels. So I will need another type of proteins to allow those large molecules to pass through the inside of the cell, from a high concentration to low concentration. Those are my protein carriers. So what is the difference between a channel and a carrier? The difference is that channels will allow small lipid insoluble substance to pass, compared to a carrier will allow a large lipid insoluble substance to pass to the inside. Did you pay energy for any of them to pass? Yes or no? What do you think?
No.
Yes, I did pay energy. No, I did not. You always remember, if you have a high concentration, you're moving down your concentration gradient to a low concentration gradient. You never pay energy. Remember, if you are all staying in this small space, you would prefer to go to your places if you don't get an extra credit, right? You will do it on your own. It's a passive. You will never prefer to stay in this small space with a high pressure. All right? So all this will be passive transports. Simple diffusion, I am passing lipid soluble substance down the concentration gradient. If I am dealing with a small substance which is lipid insoluble, you're passing through a channel, and this transport is called also diffusion. But this is a channel mediated facilitated diffusion. What I mean by channel mediated facilitated diffusion, I need a channel to facilitate the passage of the ions or the substance from their high concentration gradient to the low concentration gradient. This is still a passive transport. What about the carrier mediated facilitated diffusion? Is this an active transport? Yes or no? No. No. Still passive, but you're dealing with a large substance. It needs to be transported by a carrier. Alright? Moving on to osmosis. What's osmosis? This is the passage of water. Water. And remember that you're moving water from low solute concentration to high solute concentration. Why? Why? Because simply low solute concentration means high water concentration. And high and low solute concentration means low water concentration. What this means. So if you're looking here, so we're comparing two sides of the membrane. On this side I have 5 moles per liter. On this side I have 5 moles per 2 liters. Or let's make it 5 liters. So in other words, 5 moles per 5 liters, this is, what is the other concentration I can say? 1 mole per liter, right? So if you have 5 moles per 5 liters, this means you have 1 mole per liter, right? Yes. So which one has a higher solute concentration? This one? 1 or 2? Which one has higher solute concentration? 5 moles per liter or 1 mole per liter? 1 mole per liter will have higher solute concentrations than 5 moles per liter. So let's make it simple. So I have 5 apples, all right, in 1 liter. I have 1 apple in 1 liter. Which one has a higher concentration of apples?
Option number 1.
Which one? 1. All right. 5 apples. Of course, I have more apples per liter compared to 1 apple per liter. Right. So this will have higher concentration. Right. All right. So if I say here, I want to keep I'm not able to transport apples now through the membrane. I'm not able to move the apples on any of the both sides of the membrane. Here, what's the difference between an active process and a passive process? Can you remind me? Which one requires energy? Active process. Active process will need energy. And when do you think you will need energy to move a substance from a high concentration gradient to low concentration gradient, or from a low to high? Low to high. Low to high. You remember, always remember, when will you get all to stay in this small space? Only when you get those extra credits. So the extra credits here for the substance would be energy. I'm giving energy in the form of ATP. This is the energy currents. This is the form of energy that I will be using in my cells. So active transports, active processes will require ATP to move a substance against its concentration gradient, means from a low concentration gradient to a high concentration gradient. First example of active processes will be the active transport. So let's see on here on this diagram, you will have more potassium to the inside, you have more sodium to the outside. So you see more yellow out than in, and more green in than out. If I want to pick up the potassium from outside to the inside, and I want to move the sodium from inside to the outside. So this means I am moving against the concentration gradient. I'm trying to move the substance from low concentration to high concentration, from inside of the cell to the outside of the cell. This is the case for sodium. And from outside of the cell to the inside of the cell, this will be the case for potassium, those green particles. So how I will be able to do this, I would need a carrier, a protein carrier, which is called my sodium-potassium ATPase pump. This is how the sodium-potassium ATPase pump looks like. So it's normally directed to the inside of the cell membrane. So it has 3 sites for sodium to bind and 1 site for the ATP to bind. This is where you get your energy from. So I will be binding 3 sodium to the inside surface of the membrane pump here. I will be adding my ATP, liberating energy, and when you liberate the energy and bind the sodium, this will change the shape of the protein. And when you change the shape of the protein, now it's going to be facing to the outside. It will be facing the extracellular fluid. And as it faces the extracellular fluid, what's going to happen? You will start to release the sodium from the protein. The sodium will start to be dissociated, will get out of your cell. So what happened in here? I did move sodium from inside of the cell to the outside of the cell. From low sodium concentration to high sodium concentration. I did move against the concentration gradient. That's why it did require me to pay energy. I need ATP. So you see here, I did consume ATP to move the sodium from inside of the cell to the outside. As the protein is facing the outside, 2 binding sites will appear for potassium. Potassium here is marked green. And when you expose those binding sites of the potassium to the outside surface, 2 potassium ions will bind to the protein. And when you bind the 2 potassium to the protein, this will return the protein to its initial shape, facing the inside. And when it faces the inside, what's going to happen? It will bring the 2 potassium from outside to the inside. So what happened to the potassium? Now I did move from its low concentration gradient outside of the cell to its high concentration gradient inside of the cell. So what happened? I am moving against the concentration gradient from low to high. So again, sodium potassium ATPase pump. It has 3 sites for the sodium to bind. It has 1 site for the ATP. This is your energy. It's normally facing the inside. 3 sodium ions will bind to the binding sites on the pump, as well as ATP. When you add the ATP and the 3 sodium, this will cause a conformational change. I will have a change in the shape. Rather than facing inside like this, it will face the outside. Moving the 3 potassium from inside of the cell to the outside of the cell. When you release the 3 sodium from the sodium ATPase pump, you will be exposing 2 binding sites for the potassium. When you expose the 2 binding sites for the potassium, it will bind to 2 potassium ions, moving them from outside to the inside of your cell. So I did move the potassium from outside to the inside against the concentration gradient, from low concentration gradient to high concentration gradient. Again, is this an active or a passive transport? Active transport. It did require energy. Again, why do you need energy? Why the sodium is not passing to the inside, to the outside of the cell by itself? Why the potassium is not passing to the inside of the cell by itself? Because the substance needs to move from high concentration gradient to low concentration gradient. If you are trying to move a substance from low to high, what's going to happen? You will need to consume energy. You need to use ATP. This is what we call sodium-potassium ATPase pump. Sodium-potassium, because you are performing exchange between sodium and potassium, and ATPase, you will need to break down an ATP to liberate the energy needed to perform this conformational change of the protein. Another type of active transport, this is called my this is my vesicular transport. It's going to be divided into endocytosis. Endo means to the inside, and exocytosis. Exo means to the outside. So in endocytosis, I am moving a substance from outside of the cell to the inside of the cell. If, for example, I'm trying to move a large lipid molecule, how I will be able to do so? My cell membrane will start to eat something from outside, endocytosis, forming a vesicle that will travel to the inside of the cell. If you are trying to eat a solid particle, like for example a cell eating a bacteria, so some of your cells, some of your immune cells will allow phagocytosis. They will eat bacteria to break it down and to form an immunological memory against this bacteria for later on exposure. Alright, so here I'm eating the bacteria. This is a type of transport called vesicular transport. You're getting something from outside to the inside of the cell. This is my endocytosis. If you are eating a solid particle, this is called phagocytosis. Phago, to eat. Phago means to eat. What if you are trying to move amino acids, lipids, large molecules to the inside of the cell, which you don't have carriers for, and they cannot pass here through the cell membrane? You will try another type of endocytosis in which you will be engulfing fluid-based substance. So you get fluid, you get inside this fluid, you get the amino acids, you got the glucose, you got the proteins. You will start to engulf this fluid with the substance that you want inside a vesicle, and you will form a vesicle that will travel in your cytoplasm to be broken down, and you will be able to use those proteins, those fats later on inside your cells. The type of transport, the type of endocytosis that you're going to be using in order to get a fluid-based substance, this is called pinocytosis. pinocytosis. So again, if I'm moving a solid particle to the inside of the cell, this is called phago. If you are moving a fluid phase into a fluid phase substance, you will be using pinocytosis. Questions? So again, vesicular transport, I am forming a vesicle that would be either getting something from outside inside the cell or getting something from inside of the cell to the outside. If you are moving something from outside to the inside, this is called my endocytosis. If the substance that you're trying to move is a solid, like eating a bacteria, this is called phagocytosis. If you are getting fluid from outside, this is called pinocytosis. Pinocytosis.
This
Fluid. Pinocytosis.
is the first one.
Phago.
No,
Phago.
That's
Vesicular transport. Vesicular transport is a whole process, whether getting something in or out of the cell. If I'm getting something to the outside of the cell, this is called exocytosis. Exo means to outside. Exocytosis. Like what do you release by exocytosis? Like for example, hormones. For hormones to be released to the outside of the endocrine cells, you will form vesicles filled with this hormone, and the vesicle will start to attach itself to the plasma membrane and will become part of the plasma membrane, releasing its contents to the outside of the cell. Again, this is called exocytosis. Exocytosis. Again, both exocytosis, those are types of vesicular transport. Do you require energy to perform vesicular transport? Yes or no?
yes.
Yes, this is a type of active transport. Vesicular transport is a type of active transport. Moving on to the other parts of the cell, we have the cytoplasm. The cytoplasm is a fluid that is located between the plasma membrane and nucleus. The cytoplasm will be formed by cytosol. This is the water with solutes. Inside this fluid, you're going to have cytoplasmic organelles, and this will be the machinery, of metabolic machinery of the cells. Inside the cytoplasm, you can see inclusions. This might be granules of glycogen, pigments, lipid droplets, vacuoles, and crystals. We would be classifying the organelles into two categories. We have the membranous organelles and the non-membranous organelles according to their structure. So let's see here, first organelle that we are discussing, this is called my mitochondria. Mitochondria is a double membrane organelle, so this is a membranous organelle. It has two membranes, and it's going to be allowing the formation of energy, formation of ATP. So again, mitochondria is responsible to produce cellular energy. It's responsible to produce ATP. All right? So how do you produce ATP? Where do you get the energy from? You're going to use glucose with oxygen. You will be breaking down the glucose in the presence of oxygen. And one of the important steps will be taking place inside your mitochondria. So generally speaking, without getting into details, what is the function of mitochondria is formation of cellular energy, production of ATP. Another non-membranous organelle would be my ribosomes. Ribosomes are either membrane bound, they are attached to membranes, or they are freely scattered in the cytoplasm. Those are called my free ribosomes. So if you go back to the cell that we did start with here, you will see those dots scattered around in the cytoplasm. Those are my free ribosomes. Free ribosomes. You see another type of ribosomes, those dots here attached to this set of membranes. Those are membrane-bound ribosomes. So again, how many types of ribosomes do we have inside the cell? We have membrane-bound ribosomes and we have free ribosomes. What's the difference in terms of action between the membrane-bound ribosomes and the free ribosomes? Free ribosomes will be forming proteins that will remain inside the cell, intracellular proteins. So soluble proteins that would be located inside of the cell. Compared to the membrane-bound ribosomes, they will be attached to, as we're going to mention in a second, the rough endoplasmic reticulum, and those will form the proteins that will be incorporated with the cell membranes or that will be exported outside of the cell. Like what proteins that will be incorporated within the plasma membrane, like the integral proteins and peripheral proteins of the cell membrane. Where did you get them? You did get them from the membrane-bound ribosomes. Compared to free ribosomes, those will form the soluble proteins inside your cells. So if I'm telling you, I am releasing a protein that will be traveling to, for example, become a pigment, to form my hair color. This is called melanin. Do you think this protein will be formed from a free ribosome or membrane-bound ribosomes? It will be released outside of the cells to give you the hair color, so it is exported outside of the cell. So this would be formed by membrane-bound ribosomes. So generally speaking, what is the function of ribosomes is to produce proteins, form proteins. And again, those proteins will either remain inside your cells in soluble forms, those will be produced by free ribosomes, or they will be incorporated to the cell membrane or exported outside of the cell, those will be formed by the membrane-bound ribosomes. Moving on to another organelle, a membranous organelle. This is my endoplasmic reticulum, and the endoplasmic reticulum will be in two types. We'll have rough endoplasmic reticulum and smooth endoplasmic reticulum. So you see here, this is my rough endoplasmic reticulum. To its outer surface, you will have the ribosomes attached to it. So what do you think would be the function of the rough endoplasmic reticulum? With ribosomes and its outer surface, what do you think would be its function? If I'm telling you those are my ribosomes, so can you remind me what was the function of the ribosomes? Produce proteins, right? So here, those are the ribosomes attached to some membranes, and those membranes will allow you to produce the protein as well. Because this is where you will be forming the proteins. This is the place where the ribosomes will be forming the protein. So the function here of the rough endoplasmic reticulum will be protein formation. So what kind of proteins will be formed from the rough endoplasmic reticulum? Are those soluble proteins or those proteins incorporated and to the cell membrane and exported out of the cell? Which type of proteins will you be forming from the rough endoplasmic reticulum?
They're secreted from the side.
Outside of the cell. Or they will be here incorporated within the cell membrane. So those are produced from the membrane-bound ribosomes. Alright, so again, we have two types of ribosomes. Ribosomes scattered in the cytoplasm, those are called free ribosomes, and ribosomes attached to my rough endoplasmic reticulum membranes. Alright? What about the smooth endoplasmic reticulum? Smooth endoplasmic reticulum function will be determined according to which organ are you located in. So if we're looking at the liver, for example, the function of the smooth endoplasmic reticulum will be to metabolize lipid and cholesterol, break down the glycogen, and in the kidneys will be to detoxify the drugs, pesticides, and carcinogens. Of the functions here of the function of the smooth endoplasmic reticulum is in small intestinal cells, they will allow the absorption, synthesis, and transport of fats. In skeletal muscles and cardiac muscles, this is a site where you will be storing calcium for muscle contraction. So as we're gonna learn later on in chapter 10, we're gonna need calcium to allow the muscle contraction to take place. I will let you know at this time that you will be releasing the calcium stored inside the smooth endoplasmic reticulum of your muscle cells. Alright, so when you release the calcium into the cytoplasm, what's going to happen? You will start the muscle contraction. I will have a shortening of the length of the muscle. Alright? Moving on to another type of organelle. This is called my Golgi apparatus. A Golgi apparatus function here is to modify, concentrate, and package the proteins and lipids. So a way I would look at the Golgi apparatus is like packaging anything. So if you have a fancy diamond ring, where are you gonna put it? Well, would you put it in a plastic bag of Walmart, or would you put it in a fancy jewelry box? What do you think? Jewelry box, right? We'll put it in a fancy box. Alright, so what happens if you put this fancy ring, this diamond ring, in a plastic bag of Walmart? What's gonna happen? It will end up in trash, right?
Yes.
So what determines the fate of the ring will be the type of packaging that you've given to the ring. Same concept here for the proteins. What determines the fate of the protein is the type of packaging that it's going to be getting from the Golgi apparatus. So if, for example, I am forming enzymes that will be breaking down the fat, that will be transforming the glucose into, or breaking down bacteria. I want to keep those enzymes inside vesicles, inside my cell, for any bacterial invasion to break down those bacteria. So here, for example, I would be giving a type of packaging for the protein to remain as a lysosome inside of my cytoplasm. If, for example, you are producing a hormone, you want this hormone to be released to the outside of the cell. I want the hormone to be released to the outside of the cell. So you will be giving a packaging, a specific type of packaging that has the ability to fuse with the cell membrane to release its content to the outside, forming secretory vesicles. What if you are forming a protein that will act as a carrier or a channel in your plasma membrane? You will have to give it a specific package that allows it to integrate with the plasma membrane, to remain attached to the plasma membrane. So again, what determines the fate of the protein is the type of packaging that you will be giving from the Golgi apparatus. So again, what is the function of the Golgi apparatus will be to modify, concentrate, and package the proteins. And again, what determines the fate of the protein will be its packaging. Moving on to another membranous organelle, those are my lysosomes. Those are vesicles that will contain digestive enzymes, acid hydrolases. Where do you think I need to keep digestive enzymes in my cell? What can you eat by yourselves? What can you eat? Bacteria. So remember, I have some immune cells that will be eating the bacteria, and what you're going to do with this bacteria will be inside your cells. What you're going to do with it? Will you allow it to replicate? No, you want to break it down. So I want to digest this bacteria. How would you be able to digest the bacteria? By those digestive enzymes. So I will be using those digestive enzymes to break down the bacteria, to break down the viruses, and to detoxify toxins. Another type of membranous organelles, another function here first, other functions of the lysosomes other than breaking bacteria and viruses will be to break down glycogen. What is glycogen? Glycogen is a storage form of glucose in your liver cells. So if you did not eat something today, how your brain is functioning? How your brain is functioning, it needs glucose to function, right? So how your brain and muscle cells are functioning if you did not eat?
Slower.
You break down stores. So you will be breaking down the stores of glucose in your liver in the form of glycogen. You will be breaking down the stores of fat in your adipose tissue cells. And you will be breaking down the proteins inside your muscle cells. How would you be able to break down all those stuff? You will need enzyme. I need to have digestive enzymes inside my cells. So one of the functions here of the digestive enzymes is to break down the stored glucose in the form of glycogen and to release this glucose to the outside of the cell. Alright? Another function here for the lysosomes is to break down bones. Remember, one of the functions of the skeleton would be to provide you with minerals to maintain a normal calcium concentration. I need always to maintain a normal blood calcium concentration. How can you maintain a normal blood calcium concentration? For example, if I did not drink milk or I didn't get any source of calcium for a few days, what's going to happen? Will my heart stop beating? Yes or no? But you need calcium for your muscles to contract, right? Yeah, so how would you be able to maintain a normal blood calcium level if you didn't get calcium from outside? You will go and start to break down your bones. Those are stores of minerals. How would you be able to break down the bones? By what organelles? Lysosomes. It would be digesting the bones to release the calcium to maintain a normal blood calcium level. Another function here for lysosomes is to destroy cells. And this is called autolysis. Auto means self. Lysis means breakdown. So after a certain time, the cells will become old and they will need to die, like anything. So they will start to release the digestive enzymes from the lysosomes to break down their internal structure. This is called autolysis. Auto means self, lysis means breakdown. Another type of membranous organelles that we can see inside the cytoplasm will be my peroxisomes, and those are membranous sacs that will contain oxidases and catalases. During the metabolism, I will be forming toxins here. Those are called my free radicals. Like, for example, hydrogen peroxide. Those are dangerous for the cells. They are toxic to my cells. So if you start to accumulate free radicals in the cells without neutralizing them, your cells will start to die. So inside your cells you have sacs filled with enzymes that can detoxify the harmful free radicals that will result from the metabolic activities. Alright, so again, what is the function of peroxisomes? What is the function of the peroxisomes? I contain oxidases and catalases that will allow me to get rid of the free radicals. You don't want to accumulate free radicals in your cells because those are toxic to your cells. Your cells cannot tolerate large amounts of free radicals. So what organelle is important to produce proteins?
Okay.
Ribosomes, nucleus, mitochondria, lysosome.
Ribosomes.
Ribosomes. Okay, can you remind me what are the two types of ribosomes that we do have?
Three are
We have free ribosomes and we have membrane-bound ribosomes. Again, what's the difference in terms of function between free ribosomes and membrane-bound ribosomes? Which one will form soluble proteins that will remain in your cells? Free ribosome. Which one will form the proteins that will integrate with the plasma membrane or will be released to the outside of the cell? Those are my membrane-based, membrane-bound ribosomes. Moving on to the skeleton of the cell, those are types of non-membranous organelles. I have filaments that will build up the skeleton of my cell. Those are like my microfilaments. They will have a diameter of 7 nanometers. And they will be built by actin subunits. The protein, the building blocks of the microfilaments here will be actin. Another type of filaments that will share in the formation of my cytoskeleton will be my intermediate filaments, and those will have a larger diameter. They will have a diameter of 10 nanometers. They will be formed of protein fibers called fibrous subunits. A third type of fibers that will share in the formation of my cytoskeleton will be my microtubules, and the microtubules will have a larger diameter, around 25 nanometers, and it will be built by tubulin subunits. Part of your cytoskeleton will be your centrosomes, and those are the cell center located near the nucleus. It will be forming microtubules that will organize the mitotic spindle that we're going to discuss in a minute when we talk more about the mitosis and the cell division. Moving on to another type of structures related to the cells will be my microvilli, and those are finger-like projections that will come out of the cell membrane. The function here is to increase the surface area for absorption. So rather than having a flat surface membrane, I will have those microvilli coming out of the cell membrane. This will increase the surface area for absorption. So where do you think I would need to have microvilli? In what cells? Where do we need to absorb to perform more absorption? In what organ? Do you perform absorption from the stomach? Kidneys, you need to absorb from the kidneys. You have to allow absorption and secretion. But where else? It goes? Small intestine. Small intestine. So I will see cells with microvilli in my small intestine, in my kidney, to increase the surface area for absorption. Moving on to the nucleus. The nucleus will be formed of two membranes, two nuclear membranes. A nuclear membrane formed of two layers. I am connecting the inside of the nucleus to the outside by nuclear pores. Inside the nucleus, you will have the DNA material. This is called the chromatin. And at the center of the nucleus, you will have the nucleolus. Simply speaking, what do you keep inside the nucleus is your genetic material. And why do I have the genetic material? Why do I have genes? Why do I have DNA? So I think of DNA as like the manual of your body. So every cell will have a copy of this manual. So the manual will have many chapters, and each chapter will tell you exactly what you need to do in order to produce a specific protein. And why do I need to produce a specific protein? To have a specific character. So to express, For example, my eye color, this is due to accumulation of a certain protein. My ability to produce insulin, this is a protein. My forming hair will be a protein. The shape of my body will be determined by a protein. How big are my bones will be determined according to the proteins I will be forming. All your characters are determined by proteins produced from your cells. And what will give your cell information about how to produce those proteins will be your DNA, your genetic material, that you did get part of it from your father and part of it from your mother. So let's say this is my DNA. For example, if I am a pancreatic cell, I'm supposed to read the chapters that describes how to produce insulin. What if I get mad and I decided to read chapters which are not mine? Might become a cancer cell. Teratoma. So sometimes I might develop a teratoma. What's a teratoma? It's like a tumor that will rise from a stem cell. So I can have teratoma in the ovary, for example. So sometimes you will get hair, nails, teeth inside the ovary. Why? Simply because those cells did get mad and they start to read genetic material which they are not supposed to read. They did start to produce proteins which they are not supposed to produce. So you can find teeth inside the ovary. Alright? So again, simply speaking, what's inside the nucleus is the genetic material that describes how to produce proteins. And why do you need to produce proteins? Because you are formed of proteins. The proteins are what determine all your characters. Your intelligence, your eye colors, your body shape. All those are proteins. Alright? So the nuclear envelope here will be formed of two layers. I have an inner layer, this is called my nuclear lamina. And I have outer layers, this would be continuous with the rough endoplasmic reticulum that will be holding my ribosomes. I will have a pore complex that will regulate the transport across the nuclear envelope. So I'm passing some stuff from inside to the outside of the nucleus and from inside to the outside. Nucleolus or the nucleoli, this is where you will be producing the ribosomal RNA and the ribosomes. So usually you forget the function of the nucleolus. Again, where is the nucleolus? This is located at the center of the nucleus. The nucleolus here is responsible for the production of ribosomes. And again, what is the function of ribosomes? What's the function of the ribosomes? Function of ribosomes is to produce proteins. Produce proteins. Alright, so we can have a break for 10. We come back, start our discussion for the cell cycle and the cell division. We have permanent cells that are not able to regenerate. They are not able to divide. Can you give me an example of a permanent cell? So you have the same number of cells, they are not able to divide, you cannot increase the number of those cells. They cannot regenerate. So if you've lost one of them, you cannot build up another one instead.
Your brain.
Brain. Is this what you said?
Yeah.
Brain cells, for example, nerve cells. If I've lost a nerve cell, I cannot replace it by another nerve cell. It's a permanent cell. It doesn't go through the cell cycle like the others. What else? Like what? Heart, cardiac muscle cells. Cardiac muscle cells. If I did lose one of my cardiac muscle cells, it could be replaced with a scar tissue. You cannot rebuild the cardiac muscle cells. It's a permanent cell. So in a cell cycle, I am passing through three through two major phases. I have the interphase and I have the mitotic phase. Interphase, this is where you will be performing the growth of the cell. The cell will be growing to prepare for the cell division. This is my mitotic phase. So I will be dividing the cell cycle into two parts. You grow the cell. I need to duplicate the amount of cytoplasm. I need to increase the number of organelles. I need to duplicate my DNA, my genetic material. I need to make a copy of the genetic material in this cell for each of the daughter cells to get a copy of the DNA. All this will be taking place in my interphase. The other phase is the mitotic phase. I will be dividing the cell into two parts, giving birth to two daughter cells. I will be dividing the interphase into three phases, G1, S, and G2. G1 phase, you are growing the cell, increasing the number of organelles. In the S phase, this is where you will be duplicating the genetic material. This is where I will have DNA synthesis. Increasing the amount of DNA. I will create another copy of my DNA. And then I will keep growing the cell until I start mitosis, my mitotic phase. This is how the cell looks like in interphase. During interphase, you have a double membrane of the nucleus, nuclear membrane. The genetic material is forming this fluid-shaped appearance. This is called my chromatin. And next to the nucleus, you will have centrosomes. Those will be forming the tubules inside, as we're going to see in a minute. What happens when you start the mitotic phase? When I start mitosis, the DNA material will be condensed into chromosomes. So you see what's the difference between interphase and mitotic phase? When you start the mitotic phase, I will be condensing the chromatin into chromosomes. What else will happen when you start the mitotic division? The two centrosomes will start to migrate to the poles of the cell. And each of the centrosomes will start to form what we call the mitotic spindle. Those tubules, filaments that you will be forming inside the cytoplasm. The first phase of the mitosis, this is called my prophase. So again, what happens during prophase? You condense the chromatin material into chromosomes. Centrosomes will start to migrate to the two poles, to two opposing poles of the cell, forming mitotic spindle. During late prophase, the nuclear membrane will start to disappear. I will be degrading my nuclear membrane. And the mitotic spindle will go and will get attached to my chromosomes. Right? This is my chromosome. I'm attaching the chromosome in between, in the center, by my mitotic spindle coming out of my centrosome. What is the point at which I will be attaching the chromosomes? This is called my centromere. So again, confusing words here, confusing words. If we're looking at the cell, you have a nucleus. Outside of the nucleus, you have centrosomes, two centrosomes. Each one centrosome is formed of two centrioles. Inside the nucleus, you have chromosome. This is how the chromosome looks like. Would be again, what is a chromosome? This is a condensed genetic material. This is condensed chromatin. Each chromosome is formed of two chromatids. Those two chromatids will be attached at centromere. So those are called my centrosomes. This is called my centromere. Again, what happens here in the late prophase? In the late prophase here on the slide, we're looking at the mitotic spindle binding to the centromere. Alright? Moving on to the next phase, you start to contract the mitotic spindles. And when you start to contract the mitotic spindle, I will be arranging the chromosomes on a single line. We'll be forming a line here at the equator of the cell. This is what we call the metaphase plate. Metaphase plate. So I did contract the mitotic spindle fibers. You will be arranging the chromosomes in one single line. This is my metaphase plate. Next phase that I will pass through during my mitotic division will be anaphase. As you keep contracting the mitotic spindle fibers, you will be separating the sister chromatids of each chromosome away from the other. And I will see this V-shaped appearance, chromatids migrating to the opposing poles of the cell. So again, what happened in here? What happens? In the first phase, this is my prophase, I did condense the chromatin material into chromosomes. Each chromosome is formed of two sister chromatids, which are attached at the centromere. I start to migrate my centrosomes to two poles of the cell. The centrosomes will be forming mitotic spindle fibers. During late prophase, you will start to break down the nuclear membrane, and the mitotic spindle fibers will be binding the chromosomes at the centromere. You start to contract the mitotic spindle fibers. You will be arranging the centromeres at one line. Here, this is called my metaphase plate. This is taking place during metaphase. As you keep contracting the mitotic spindles, here I will be separating the two sister chromatids away from each other. So I will be moving the chromatids to the two poles of my cell. This is called anaphase. Anaphase. After anaphase, I will pass through the last phase of mitosis. Here, this is called my telophase. Telophase, what happens? You start to break down the mitotic spindles. The nuclear membrane will start to reappear. The nucleolus will start to reappear another time, and the chromosome will return back to the chromatin shape. During telophase, you will start to form the constricting ring between the two poles of the cell, separating the cell into two daughter cells. This here is called my cytokinesis. Cytokinesis begins during late anaphase. I will form a ring of actin microfilaments that will contract, forming a cleavage, and will be dividing the cell into two daughter cells. So again, what is the word that we use to describe nuclear division? This is mitosis. All those steps: prophase, metaphase, anaphase, and telophase. All the four steps are called mitosis. This is nuclear division. What we call the cellular division, what do we call the cellular division? For the cell to divide into two daughter cells, this is called cytokinesis. cytokinesis. Again, very common mistakes that you usually do on the test. When I ask about cell division, your answer will be mitosis. This is the wrong answer. Right? Mitosis is nuclear division. Nuclear division. Alright, what is cell division is called? Cell division is called cytokinesis. Cytokinesis. Alright, so during what stage of the cell cycle is DNA replicated? What do you think? So which phase during which you will be replicating the DNA, the genetic material? Are you replicating the DNA during division? Yes or no? During mitotic division. What do you think? When are you duplicating the DNA or genetic material? Which phase? Interphase. Interphase. Remember, cell cycle is divided into two parts. Cell cycle is divided into two parts. We have the interphase. This is where the growth of the cell will be taking place, and this includes the duplication of the DNA material. This is called my interphase. Then we have the mitotic division, or mitotic phase. Here, this is my mitotic phase. This is when the cell is divided into two cells. Alright, so remember, what are the three phases of the interphase? G1, S, and G2. G1, S, and G2. Which one of the three where you will be duplicating the DNA? G1 or S or G2? S phase. So DNA is duplicated again during interphase, again in my S phase of the interphase. Here, the mitosis here it will be prophase, followed by first, before you divide, you will be arranging them. So this will be metaphase. Then you'll separate the two chromatids, anaphase, and then telophase. This will be followed by the separation of the two parts of the cell into two daughter cells. This will be called my cytokinase. Right? All what we've mentioned here is taking place during the mitotic phase. Alright? So let's see this video on here. Shows the different steps of mitosis.
Mitosis. Mitosis is a process of cell division that makes possible regeneration of body parts. To elaborate, mitosis is the separation of nuclear chromosomes into two identical daughter nuclei. It is divided into four key phases: prophase, metaphase, anaphase, and telophase. An additional phase called cytokinesis occurs after the complete nuclear division. Before a dividing cell enters mitosis, it undergoes a period of growth and rest. This period is called interphase. In interphase, the genetic material of a cell increases. Prophase. During prophase, the chromatin condenses and becomes short and thick to form chromosomes. Each chromosome has two sister chromatids joined together at the centromere. The nucleolus disappears and the nuclear membrane starts to break down. The centrosomes, each with a pair of centrioles, move apart to the opposite poles, forming a spindle between them. Metaphase. During metaphase, microtubules of the spindle interact with chromosomes. This causes the chromosomes to move and align along the middle of the cell or the equatorial plate. Sister chromatids are held at the centromere, confirming the presence of protein structures called kinetochore at the surface. The kinetochore holds the chromosomes and attaches them to the spindle. Anaphase. During anaphase, the sister chromatids separate at the kinetochores and the daughter chromosomes, along with the divided centromere, move towards the opposite poles as the microtubule shortens. The poles of the spindle also move apart and help to separate the chromosomes. As the chromosomes separate completely into two sets, one at each pole, anaphase is considered complete. Telophase. During telophase, the daughter chromosomes arrive at the pole and the chromatin starts to decoil. Also, the nuclei reform along with nucleoli. This triggers the reformation of the nuclear membrane. Cytokinesis. Cytokinesis is the partition of the cytoplasm. In animals, a cleavage furrow appears in the plasma membrane, which deepens and divides the cytoplasm into two daughter cells, each containing a nucleus. In plants, new cell wall formation is triggered at the center of the cell by the formation of the cell plate. The cell plate grows outwards till it meets the existing wall, resulting in two daughter cells. In this module, you have learned mitosis is the process of separation of nuclear chromosomes into two identical daughter nuclei. Mitosis involves four key phases: prophase, metaphase, anaphase, and telophase. In prophase, the chromatin condenses and becomes short and thick to form the chromosomes. In metaphase, microtubules of the spindle interact with the chromosomes. In anaphase, the sister chromatids separate out at the centromere and move towards the opposite poles as the microtubule becomes shorter. In telophase, daughter chromosomes arrive at the pole.
Any questions for me at this point? Any questions? Alright, so let's move on very important topic here. So, as we've mentioned, we need ribosomes to produce proteins. Where do you get the information on how to build up those proteins from the genetic materials that you keep inside the nucleus with chromatin, your chromosomes? This is where I keep my genetic material. But how will I be able to form a protein out of this genetic materials that I keep inside the nucleus? I need to pass through two processes. First one is called my transcription. I need to get the codes that will be describing here how to produce a protein on a message. This is called my messenger RNA. The messenger RNA will travel to the outside of the nucleus. This is where it will meet with the ribosomes. Will be conducting the codes to the ribosomes, and according to which the ribosomes will keep adding amino acids, and according to the sequence of amino acids that you will be adding together, you will be building up a specific protein. So what does this mean? This means that any of your proteins are formed of the same basic subunits. So for example, if I am looking at a cell membrane carrier. I'm looking at the cell membrane channel. I'm looking at insulin. I'm looking at my hair. I'm looking at my nails. I'm looking at insulin. All those are formed of the same 20 types of amino acids that we do have in nature. All those different structures are built up by 20 types of amino acids. But the difference between one protein and the other would be the sequence of arrangement of those amino acids. And again, what did determine the sequence of arrangement of those amino acids would be the genes on your DNA. So again, in order to get the signals here, or the message on how to form a protein from the DNA, you need first to form what we call a messenger RNA. You send a message from your DNA to the ribosomes. Again, formation of a messenger RNA is called transcription. Transcription. Your ability to read the sequence on the messenger RNA and to produce a polypeptide chain, a protein, according to the sequence on the messenger RNA, it's called translation. Translation. It's like moving, it's like decoding or transforming one language to another. I'm using, from what I'm using here, I'm using the nucleotides, the DNA, and I'm using here, I will transform this language into another language. This is in which I will be using amino acids to build up proteins. Right? That's why I called it translation. It's like using a different language. Those are highly testable concepts in your HESI test, in your TEAS if you're applying for nursing, of course for PCAT, MCAT, for those who are applying for pharmacy, for those who are applying for medical school and stuff like that. Very important information again. Very important and very basic actually. So transcription is the formation of a messenger RNA from DNA and the formation of a protein chain according to the message on the messenger RNA. This is what we call again translation. What's the DNA structure? The DNA structure, I am formed of nucleotides. I am a double-stranded molecule which is closely packaged inside the nucleus in the form of chromosomes, like what you see here. What are the building blocks of those nucleotides? The nucleotide will be formed of a pentose sugar. What I mean by penta means 5. So this is a 5-carbon sugar. I'm formed of a 5-carbon sugar. I have a phosphate group attached to the 5-carbon sugar, and I have a nitrogenous base also attached to the 5-carbon sugar. So again, 3 basic structures here that will build up the nucleotides of my DNA. I have pentose sugar in the form of deoxyribose, phosphate group, nitrogenous base. We have 4 types of nitrogenous bases that are paired together. What this means that on one side, for example, if you have adenine, on the other strand of the DNA, it has to be attached to thymine. They are anti-parallel, complementary. Adenine will bind to thymine. If you have guanine, this has to be bound to cytosol. So let's see here. How a nucleotide building of the DNA looks like. I'm a pentose sugar, so I am formed of 5 carbons. So this is carbon 1, 2, 3, 4, and this would be 5. Attached to those 5 carbons, I will be numbering them. like this, 1, 2, 3, 4, and 5. I will have a phosphate group which is usually negatively charged. And here I will have a base attached to it. So I have two things attached to the pentose sugar. You have a nitrogenous base and you have a phosphate group. What are the different bases that we might see on a DNA molecule, on the nucleotide of a DNA? Either it would be a purine, like adenine and guanine, or it would be a pyrimidine, like cytosine and thymine. What we need to understand is that the DNA is a double membrane. I'm sorry, not a double membrane. No. A double molecule like this. I have a nucleotide, and on the other side I have another nucleotide paired with it. Those two strands of the DNA are paired by hydrogen bonds. Those hydrogen bonds that I'm marking as dotted lines. I am attaching bases together. So on this side I'm attaching the base to the other side. How will I be able to pair them? Adenine will be paired with thymine. Guanine will pair with cytosine. So if I give you the bases on this strand, can you give me the bases on the opposite strand? What do you think? What's going to be on the opposite strand? So A is paired with? T is paired with? A. C is paired with? Guanine. Guanine. Cytosine.
C.
Cytosine.
T.
Thymine.
A.
Adenine.
G.
Guanine. Cytosine, and guanine. Alright, so what determines the codes here for the amino acids are called codons. Every three bases will form a code. Every three bases are forming one code. I need to transform the DNA into RNA by a reaction that we called, again, this is called transcription. I need to get a messenger RNA from this DNA. So a DNA is a double-stranded and RNA is a single-stranded. So let's say here, what we're going to have on the RNA, RNA won't have thymine in its structure, instead it will have another base, it's called uracil. So if I'm getting the codes, I will use this side, this strand, as a template for the formation of a messenger RNA. So I will be using A will be paired with U, T will be paired with A, G, next will be, here J will be formed, C, then do you have T on the RNA? No, you have
U.
uracil instead. You have U. Then T will be paired with adenine, guanine, cytosine, and another guanine. This is my messenger RNA. Those are the codes that I would have on the messenger RNA. How would I be able to use those messages, those codons on my messenger RNA? I would need to pass the messenger RNA through my ribosome. Let's see here. This is my ribosome. This is how it looks like. I have two subunits. The messenger RNA now is passing through the ribosome between its two subunits. So what is the first code that we've got on the messenger RNA is U. Can you tell me? A, G. This is the first code. Every code is formed of 3 bases. Next code is GCC. Then will be UAG. So let's imagine here, ribosome will be calling somebody to get a corresponding amino acid from inside of the cell. The type of molecules that will be carrying the amino acids to the ribosomes, those are called my transfer RNA. Those are carrying the amino acids, the building blocks of the proteins. So let's see here. Can you find in the table in front of you UAG? UAG.
Base A.
This is a stop codon. This is a stop codon. It's not coding for any of the amino acids that I do have. So what's going to happen? I will not get any amino acid at this position in the protein. I won't be getting any amino acids. This is a stop codon. What about the next one? GCC. GCC. Alanine. So I will be calling for alanine. We'll be trying to get the transfer RNA to the site here where I have an amino acid carried on it called alanine. This will be the first amino acid in my polypeptide chain. And then according to the sequence of codons that I have on the messenger RNA, I will be adding amino acids together, forming a polypeptide chain, forming a chain of amino acids. I will be creating bonds between those amino acids called peptide bonds. And as we're going to see in chapter 2 later on, if this is here, for example, this is my polypeptide chain. I have a chain of amino acids. What will be determining the function of a protein is its shape. So some of the amino acids will have positive charge site. Some of the others will have negatively charged site. So what's going to happen between a positive and a negative? Will they move away from each other, or I will have attraction between them? I will have attraction, right? If, for example, I have this part of the polypeptide chain, it's formed by an amino acid that hates water. It's hydrophobic. So what's going to happen? Will it move to the outside of the molecule, or will it move to the inside of the molecule away from water? It will move to the inside of the molecule. So you see here, what did determine the shape of the protein is sequence of amino acids. And what did determine the sequence of amino acids? The sequence of codons that you've got on your messenger RNA. And what did determine the sequence of codons on the messenger RNA is your DNA. So again, the whole story here, you do have the codes, the genes, that are showing you how to produce all the proteins in your body. On molecules called DNA, double-stranded molecules. You will be getting those codes from the DNA to get outside of the nucleus as a message called a messenger RNA. This messenger RNA will pass inside an organelle, a non-membranous organelle. This is called my ribosome. Ribosomes' function here is to read, simply speaking, is to read the code and call for the corresponding amino acid according to this table. Who will be transporting the amino acid for me? This is another type of RNA called transfer RNA or tRNA. So for example, as we've seen here, if you have a code on the messenger RNA GCC, I will be calling for alanine, one of the types of amino acids. Be getting alanine at this position. Next code, I will call for another amino acid. We'll get it to the next position. We'll attach those amino acids together, forming polypeptide chain. Chain of amino acids. Is this a functioning protein? No, it's not. Again, what determines the function of the protein is its shape. And what determines the shape is the sequence of amino acids. So according to the charges, according to whether those amino acids are hydrophilic, hydrophobic, you will be changing the shape, forming a three-dimensional structure of the protein. And this three-dimensional structure will act as what we've seen earlier today. It might act as a channel, it might act as a carrier, it might act as a sodium-potassium ATPase pump, it might act as a hormone, a chemical message, an enzyme, it might do anything. So again, what did determine the function is shape of the protein. And what did determine the shape of the protein is sequence of amino acids. And where did you know the sequence of amino acids to produce this protein? Is the codes on the messenger RNAs that you've got from your DNA. What if I have a mutation? What's a mutation, for example? I have a malformed protein. It might pass unnoticed. This is called a silent mutation. Or it might cause a disease, like sickle cell anemia. What's sickle cell anemia? What's the problem with sickle cell anemia? I have a protein inside my red blood cells which is supposed to carry oxygen. Because I did change one of the amino acids, here I did change it, I did replace it by another amino acid, this caused a deformed protein. And as a result, my cells are start to sickle. I will form those sickle-shaped cells. Instead, if you remember, when we did discuss in the tissues, those red blood cells are biconcave discs. Rather than having this shape, I have those sickle-shaped cells. So they are blocking my blood vessels. I'm not able to deliver enough blood to my tissues because of the shape of the cell. What did cause this disturbance in the shape of the cell? Malformed protein inside the cell. I did replace just one amino acid by another. So rather than reading, for example, ACU, I will read AAU. So what's going to happen? I did change the type of amino acid I am putting in this protein. And if they change the sequence or the structure of the amino acids, what's going to happen to the protein? It might lose its function. If it loses its shape, it might lose its function. Right. So what you're going to do after you form the protein? After you form the protein in your ribosomes, whether they are, especially for those which are produced from a membrane-bound protein, membrane-bound ribosomes. What you're going to do with those proteins, after you get those proteins, those large polypeptide chains, what you're going to do with them? Remember what you're going to do with this fancy ring? Packaging. What organelle was responsible for packaging, modifying, and concentrating the proteins? Golgi apparatus. Golgi apparatus. So the protein will need to be modified. It needs to be condensed, and it needs to be packaged. And according to the type of packaging, whether it will integrate with the cell membrane, it will remain inside the vesicle, inside your cytoplasm, or will be released to the outside. Three main types of RNAs that we're looking at. We did see two of them, while actually we did see all the three of them today. Messenger RNA, this molecules that will be formed from your DNA by transcription to send the message to the ribosomes. This is where the proteins will be formed. Another type of RNA, this is my ribosomal RNA. Ribosomal RNA. And this is the building blocks of the ribosome itself. Ribosome itself is formed by ribosomal RNA. The transferred RNA, those are the molecules that will be binding to the amino acids and will pair them with the codons on the messenger RNA inside the ribosome. Again, 3 types of RNA. We've seen messenger RNA that will be carrying the message out here. From the DNA to the outside, carrying those codes. Ribosomal RNA, this is the RNA that will be building the ribosomes. Transfer RNA is a molecule here that will be carrying the amino acids corresponding to the codons on the messenger RNA. We'll keep adding them together to form this polypeptide chain, this protein. Questions? Alright, so that's it for today. So I will be canceling chapter 2 from this coming test on Monday. We don't have this Monday, the test on this Monday, we're going to have it next week. Alright, so I will be canceling chapter 2 from this test. And we're going to do an extra session covering chapter 2 on Saturday. Alright, I will tell you the exact time and class. I need to give this notification for all the people in class. Alright, thank you so much. Have a good rest of your weekend.